Hello and welcome to this Geographic Calculator webinar for May 2015. Currently all attendees are in listen-only mode and you should be able to see our first slide on your screen. I'm Josie Wilford, an Applications Specialist here at Blue Marble Geographics. I'm here with Sam Knight, the Director of Product Management.
Okay, good afternoon everyone. Today's topic is going to be Geographic Calculator 2015, and specifically we're going to be working with local coordinate system data. So the interfaces we're going to be taking a look at today are mainly in the best fit functions of the point database conversions job. Mostly what we're going to be doing is mapping up local survey coordinate system data against a geodetic control base and establishing a transformation to get from these ground grid style systems into something geodetically based that we can put into a common GIS system, or that we can navigate through with something like a GPS, for example. We're going to be taking a quick look around on the interactive conversions job, some of the data source dialogues as well. But as a bonus today, we're coming back with one of our live sessions, and the reason for that today is we've just recently launched Service Pack 1 for Geographic Calculator 2015. This is going to be the service pack for the year until the next major release. So we're going to start off today. We're going to spend the first 5 or 10 minutes talking about some of the new features that we've just added into the service pack. And then we're going to get rolling into the real meat and potatoes here today of working with those local coordinate systems. If you like our videos here today, we have largely transitioned over to a pre-recorded format of videos. Today is one of our live exceptions to that. You can find our webinars page right on our main site. We have a YouTube channel that we link to from there, so you can subscribe to our YouTube channel directly. See all of our pre-recorded videos that we push out. Subscribe, like, watch, and we also have comprehensive training available if you want to go in much deeper detail than we get into in some of these videos. You'll see both of those web addresses right on your screen, and again, both easily accessible right from the main page of our website.
Alright, so if you have any questions today during the presentation, you can use the questions tool on the GoToWebinar panel to the right of your screen. We will try to answer your questions as they are submitted, and Sam will address any outstanding questions at the end of the presentation. And as always, you can contact us at geohelp@bluemarblegeo.com for further information after the session. We have some upcoming events, and I'll just hand over to Sam so he can tell you a bit about those.
Okay, so we're going to be at a few more conferences. We've already been at a few conferences so far in May, and we've got 3 more coming up very shortly here. So next week on the 17th, we're going to be at the Digital Mapping Techniques Workshop. That's being hosted by the Association of American Geologists Conference in conjunction with the USGS out in Salt Lake City, Utah. Also next week, we'll have representatives at the EnerGIS conference in Canonsburg, PA, and also at the end of the month, we'll be at the GeoBusiness 2015 conference. That's going to be over in London in the United Kingdom. We have many more conferences and events that we'll be at throughout the upcoming months and throughout the rest of the year. At the bottom of the page there, you can see the link to our events page, and this is where you can find out where we'll be coming to a part of the world that might be a little bit nearer to where your location is. As well, we have just recently launched a brand new website on our page for the Blue Marble User Conference, and that's our annual user conference. The location of that moves around. We've had it in Texas, we've had it in Colorado, we've had it up in Calgary. The location for that rotates around. This year we will be having our user conference in Arlington, Virginia. And that's going to be coming up in October 6th. Brand new site on our main website there for the user conference for the year. We have also just opened the call for presentations on the website for that. So if you have any use of Geographic Calculator or Global Mapper or any of the Blue Marble tools that you might be using, feel free to submit a presentation. Tell us and tell the rest of the user community what kind of interesting stuff you're doing with some of these tools. So again, Blue Marble User Conference also coming up on October 6th, Arlington, Virginia. So to roll over here, today we're going to be working in the Geographic Calculator. Give me just a second here. I'm going to be bringing up our questions panel so that we can track any questions that you send in while we're going along here. And as I mentioned, we're going to start off by going through some of the newer features that we've added here in the service pack. We're going to take just 5 or 10 minutes to start off with here. So what have we got first on our list, Josie?
Okay, let's see. We've added a Save As option to the interactive calculator.
Okay, the Save As function. This is a nice little quality check, nice quick way to get coordinate data out of our interactive conversions job. So I happen to have my interactive conversions job open here on the interface, and I have some coordinate data already saved into this job. Now, if I wanted to take a look at this and see where my conversion was coming out spatially, I would need to go to a GIS application. A lot of folks use Google Earth for just very, very quick checks. If you want to do a little more precise check in a true GIS system, we needed to make it a little easier to do that rather than just taking the numbers out of the interface here. So what you'll see is a new right-click option. So when you have your converted data on either side, either the input or the output, in the right-click context menu for the coordinate point definition, you're going to see a new option for Save As. And if you click that Save As option, what that's going to do is allow you to save that point out as a spatial file, such as an Esri shape, and that file is going to come out containing a single point. You can load that off into the GIS system of your choice, compare it to your other control data, and get your quick check done that way. So just another quality check method that we've added in there.
Great, thanks, Sam. We've also added a new method for calculating forward and inverse distances above or below the ellipsoid. Can you tell us a bit about that?
Okay, so the new math that we've added into the forward and inverse functions, this was a feature that was suggested to us by one of our users, and he was kind enough to point us at some improved math that we could do for this. Forward and inverse are basically standard mathematical functions that we can step through. The math is simply called forward and inverse math. It's an ellipsoidal calculation, so that means it usually takes place right on the surface of the ellipsoid, so at ellipsoid height 0. As a part of that, if you put your interactive job into forward or inverse mode, you would see the coordinate systems simplify. First of all, the datum transformation disappears in the center, and that still happens because this happens on the surface of a single datum. But also the vertical reference would disappear in forward and inverse mode. You'll notice that now when you put it in forward or inverse mode, you have the vertical boxes enabled, and that allows you to select an ellipsoid height for your coordinates. So you can not only specify your latitude or longitude or northing or easting, but you can now also specify an ellipsoid height with those values, and the ellipsoid height will be factored in to the distance that is calculated between your starting point and your ending point, both in the context of forward and inverse. Some folks are going to find that useful, probably mainly surveyors that are working at elevation. This was the user that pointed this out to us, is a surveyor that works out west, spends a lot of time at elevation where there's a lot of extra math you have to figure in when you're doing ellipsoid distance calculations, just because of the vertical distortion that is also brought in from those heights. So this is just as simple as adding in your ellipsoid heights to your coordinates, and they will affect the output proportionally.
Great. So the Geodetic data source now supports the Epsg history and revision dates. Can you tell us a bit about the benefits of those? Okay,
so this is going to be a new feature that's going to help out folks that are very often working with what I'm just going to call some of the more esoteric systems in the Epsg database. As we're navigating through, so what I'm going to do here is open the information for the NAD27 system I have specified. In the information dialogues for these, we've had the identifications, we've had the definitions where you actually find the parameters, and those have been the two standard pages that we have. So there's been a lot of information on those. We've had the identifiers that allow us to cross-reference those into other databases. We've had the remarks from the EPSG database that help us get a little bit more context for some of those systems. Obviously, the definitions are very important, the parameters themselves, but this new tab that we've added is the EPSG history for a particular definition. So all EPSG entities can have a revision history for them. This is stored in the EPSG database, and this is something that you might have had to research when working with older systems, things that are a little more rare that you might not be as comfortable working with as sort of some of the more modern regular systems. But essentially, what these are they have revision dates where things have been altered or updated or changed over the years within the context of the EPSG database. You'll find information like the original person that reported those. Every once in a while, you might even actually need to contact somebody and find out what a particular revision was for. A summary of the original change request into the EPSG database, and then as well, a quick description of the changes that were made at that point. And then as well, at the bottom there, you'll see some notes on any affected EPSG codes. So this gives you a very quick way to do a little bit more historical research on the changes that have actually taken place in the EPSG database. A related question here that just popped up. Does Geographic Calculator have a direct connection to the live EPSG database, or is it static to the current version of Calculator? So that's a very, very good related question. We do actually have a live connection that you can use to update your EPSG database. That's going to be found under the Data Source menu. Down towards the bottom, you'll see Import Objects from the EPSG Registry. That is a tool that you can use to get updated definitions, anything that's been added new since we've last released Geographic Calculator. It is a static database, so the database itself does live on your local installation, and it will remain the same until you actually choose to update it through that live update. And the way that works is you pick the individual definitions that you want to bring down. You don't need to bring down everything unless you actually want to, but there is that live capability in there. I believe we actually do have some of our other older webinars, I think, actually get into that topic as we're covering some of the administrative functions in some of our older webinar sessions. So maybe take a look at our YouTube channel to find out a little bit more about those connections.
Okay, great. We've also added a search tool to the transformation dialog. So let's cover that.
Okay, the search tool on the transformations dialog. So our transformation dialog in the center is where we go to get all of our datum transformations, and that has all of the tools built in that we're used to for seeing exactly where a particular transformation applies, all of the information like the accuracies, the area of use for those transformations, and the general names, things like EPSG codes. We've never actually had our search tool available on this dialog before. We've presented a narrowed list, and it's been technically under the hood. It's been a little tricky for us to add search to that. But recently we've figured out a good way to do this, and so now we can actually filter down through that short list of results. So what this one is mainly useful for is if you have a combination of datums that doesn't take it all the way down so that you just have one obvious choice. If you've been told you need to use a particular transformation, the search tool makes it very, very quick to do that. So just as an example here, for my transformation between NAD27 and my NAD83 system, I see a bunch of EPSG codes on the end there. So let's say, for example, that I've been told that I have to use the transformation with EPSG code 1241. And if I have a list that's even longer than this that's coming up, all I have to do is just enter 1241 down here in my search panel and hit search. That's going to narrow that list down to just that one transformation It also works on text searches. You can search in any of those specific columns that you have. If you have custom names for things from your proprietary enterprise database of coordinate systems, it can make it very, very quick to narrow that list down, whether it's a short list or you have a long list of possible combinations for a certain set of systems.
Okay, we've also added the ability to assign elevation attributes to the geometry for output vector data.
Okay, this is a nice little quick one. On our vector data conversions job, you're going to see a new checkbox setting right up here. So this gives us the ability to take a 2D vector file that has an attached attribute table. When we toggle this on, it's going to enable this drop-down that lets you visualize all of the column names in that attribute table that's attached to the file. If one of those attributes columns has elevations, you can use this to specify that as the elevation for the file. So that allows you to directly take a 2D file that has elevations, maybe something like a contours layer that's been derived for an area. It allows you to apply those z coordinates and directly output a 3D vector file as a part of your transformation. So that's just another nice little quick one in there. And among others, we do have more than that. We just wanted to take a few minutes to talk about some of those latest new features.
Great. We've also added some new geodetic definitions and methods. Do you want to tell us about anything notable there?
Yeah, so in our What's New list, you'll see there's a number of new methods of things like geoid and vertical transformations, new projections, and things like that. Some of the notable contents in there for our US users, we've recently added support for the National Geodetic Survey GeoCon system. Those are transformations between NAT83 HARN, NSRS 2007, and NSRS 2011. Those are going to be very helpful for US-based surveyors. Additionally, for folks in the U.S., we've just added the recently released Geoid 12B for the United States. That's going to be another very popular one. Beyond that, we've added a number of vertical systems around the world, vertical slope transformations, a new Japanese geoid, some Dutch transformations. There's a new cartographic projection called Patterson that is a new product of Tom Patterson, who works with the National Park Service here in the U.S. That's a new cartographic world projection that's available. And lastly, I just want to draw attention to the magnetic declination models that we've added as well. So in our big release for the year back in December, we released support for magnetic declination. That's a new option in the Preferences dialog to display magnetic declination for interactive conversions. With that, we had one model embedded, and it was a model that was a little more limited than some of the ones we've just added that really flesh out the support. We've now added several world models that you can choose from via this drop-down that allows you to choose from the common world magnetic models or some of the other common international models that stretch into much, much larger date ranges and are truly global models so that they can be used anywhere on the planet. So that's going to do it for some of our new features. And as promised, now we're going to roll over and actually get into working with local coordinate system data. So again, if you have any questions as we're going along, feel free to use that questions interface to submit those, and we'll take some as we go. And if we don't get to them all, we'll take some time at the end to finish those up. So today we are going to be moving over to the point database job, and what this session is going to be all about is taking non-geodetically based systems and deriving a transformation that lets us do this. The data that we're going to be talking about is mainly going to be coming from surveyors. So surveyors working in local ground grids where we have arbitrary distances, arbitrary origin. Things are based on local landmarks such as a pin in the ground measured in surface distances away from that first origin location. The data that we have here is actually real data that came from an oil field, and we've simply moved this data spatially at an arbitrary amount to generalize it. So this is real survey data that originally came from an oil field project. And so we're going to be stepping through numbers that are fairly common, fairly similar in terms of accuracy and things like that.
Okay, what do I need to set up one of these systems?
Okay, so much like the data that we're going to be working with today here, the minimum that we need is a table of control points. So most commonly, a lot of folks are working with things like an Excel sheet or a comma-separated sheet, and the sheet itself, the absolute minimum that you need to have in that sheet is 4 columns of coordinate data. We're going to have 2 columns that represent your local northings and local eastings, and 2 more columns that represent something geodetically based. So it can either be a latitude-longitude or it could be a northing and easting. In the case of the data we're looking at today, our control data is in UTM zone 15 north on WGS 84. Just as easily, this could be based on state plane, could be based on a UTM system such as we have here, or it could be based on any projection or latitude-longitude based systems.
Okay. How many points would I actually need to do this?
Okay, so that's one of the more important questions here. In today's data set that we're looking at, we have about 28 points in this control set. The area that we're looking at is a couple thousand yards across. It's a fairly localized area, and that's generally true of your typical survey systems. Some of these that we might bump into in the world do stretch over miles and miles. I think the largest one of these I've ever worked on myself actually stretched over, I think it was about 11 miles. That's a pretty big area for a ground-based survey grid. Most of these are going to be a couple of miles across in the max. Where we find these things are in large engineering projects, things like some kind of manufacturing plant facility where you have very large buildings, very large engineering plans tying everything together. Airports are an extremely common place to find these. Just about every airport has a local survey ground grid that they use for mapping those out in the highest local precision available. Mining areas typically have these, since GPS type coordinates don't work well underground. GPSs totally fail underground, so everything is done in a local reference type system. So the base data that we have here, I said we have about 28 control points. In practice, the absolute minimum that you need for one of these is 3 control points. Keeping in mind that 3 control points is not necessarily going to get you a very tight fit. Up to about 30 to 50 is generally the max you might need to worry about. If you were going to be using an extremely high order polynomial, and we'll get to those in just a few minutes, you could go up towards 100 control points. But generally, for good return on your time, somewhere between 20 to 50 control points will deliver very reasonable results for these. So for my data today, our control was derived by a surveyor based on local ground measurements. They happened to conduct their survey in UTM zone 15 in meters, and so that's what we're going to be used. Where those control pairs actually come from is based on the ground. So you essentially do your local survey in both systems. So you have your origin is going to be some arbitrary location. It might be a pin in the ground. On some property areas, it could be something like a rock or a tree even. But that's going to have some arbitrary local coordinate that has been assigned to it. Those only mean anything in the context of that local grid. The control coordinates for those are also going to be the result of either a traditional ground survey based on distance and azimuth between those points to calculate your local ground coordinates, or a more modern survey technique is going to be to GPS survey all of those local system coordinates to establish a GPS-based control pair for those. So what we have on each line is the same point represented against both systems. So one in our local control and one in our geodetically based control. You're going to see on my sheet here that I've got a bunch of extra placeholder columns. Those columns are not actually needed as a part of your base data. We can set those up as we're stepping through the column settings. So again, the bare minimum you need are these 4 columns of local northing and local easting and a UTM northing, and in my case it's UTM, but a geodetically based control pair, northing and easting, or latitude longitude to go along with those. Now when we click our interface into the best fit mode, you're going to see the datum transformation box disappear from the center of that interface. And you're going to see a control system on the right, and you're going to see a blank new fitted coordinate system on the left. This is just our placeholder where we're eventually going to add in our own custom name for that system. So for this derivation, we're basing this on UTM zone 15. So I need to set that up as my control system on the right. So I'm going to double click to select a coordinate system just like I normally would. And I'm going to browse down under our projected list into UTM to find the zone 15 north based on WGS 84 in meters, which is what my control points are all in. The system on the left we don't actually need to worry about at this point because it has nothing in it. It's essentially going to be a blank system. And what we're going to be doing as a part of this is filling out the parameters of this that are going to be a polynomial equation that's going to get us from our local system to our control system. So at this point we can hop into our column settings, and this is typically where you're going to be adding these placeholder columns. So in the dialog that pops up, you'll see where our settings say point database settings best fit. Depending on which operation you have specified at the bottom down there, this is going to say things like convert, forward, inverse, depending on what function you have selection. And so it's going to say best fit when we're actually doing one of these derivations. Now the columns for input here are going to be our original coordinates. Those are the local coordinates that we're matching up. In the drop-downs, you're going to see all of the heading names that come in from your data. So this data sheet that I have came in from an Excel sheet with those column headings in there. If you are working with data that doesn't actually have clean headings in there, you're going to see simple things like C1, C2, and C3, so on, across the sheet. I typically recommend actually renaming those, getting the column headers in there before starting this process, just because best fit is one of the things that it's one of the more comprehensive, complex things to set up in here. There's a lot of columns that we're going to be dealing with, so it's usually a pretty good idea to have the appropriate column names already set up for yourself in the top. So here I'm just going to match up that my local northing and local easting correspond to the original coordinate fields. Those are going to be tagged northing and easting. Your transform coordinates are your control systems, the geodetically based systems, and those are going to correspond to, in my case, the UTM 15 north and UTM 15 east columns that I have in my spreadsheet. Those are going to be tagged northing and easting as well, if you are using a projected coordinate system as the control system. If you have latitude and longitude based systems, so geographic coordinates, those would be instead tagged latitude and longitude for your control. Now that's all you need to actually start with. The rest of this can be filled in as you go. Again, I have placeholders already set up for those. Some folks like to do that. Some folks would rather just add them as they go. Getting down to the point use flag. This is a column that typically you're going to create with your data. I've already added mine in. You'll see that point use flag column in the table. It's full of ones, and at the top I've just simply titled mine point use flag. When you add that column in using the add button right there, what that's going to do is create a new column and populate it all with ones. And that column is going to act as an on or off switch for a particular control pair. I'm going to come back to that. That makes a little bit more sense after we've done the first derivation and we start taking points in and out, and you'll see how that ties in. An optional column that we have is point name. Very common in survey control data. You're going to have a particular ID associated with a point. You can assign a column to that if you have one. In this case, my data didn't actually have a point ID column associated with it. So I'm going to leave that set to none for my case. And in the map that I'm going to generate here, we're going to see that all of our individual point rows that we have in our table, they're simply going to be identified by the row number that they appear on. So there's no detriment to not having a point ID associated, but if you are working with a survey system that has that, it's perfectly fine to use it as well. Down at the math transform, this is where you have a choice to make. This is the polynomial model that we're going to be working with. I'm going to sum this up by saying each one is more complex than the one that comes before it. Basically, each one is going up by an order of magnitude of complexity in the math of the polynomial that is starting off with it. An affine model is a simple 3-point required linear model. The mathematics under the hood of it actually look very similar to the slope of a line on a graph. If you're familiar with the old slope of a line equation, y equals mx plus b from Algebra 1 in middle school or high school, that's going to be very, very familiar looking math in there. It's got essentially two versions of that equation back to back, one for the x coordinates and one for the y coordinates. From there, it goes up into polynomial-based math. So the affine is a linear model. The second order polynomial basically adds an x squared into that equation, and the mathematics resemble the mathematics of mapping a parabola on a graph. From there, third order, fourth order, fifth order, basically just getting more and more complex in the polynomial that is being derived. For each order we increase, basically what happens there is we add in one mathematical curve that we can straighten out in the best fit relationship. Some general guidelines in here. If you're working on a typical local survey of an area, you're getting out into areas that are just a few miles across. So I'll say, up to about anywhere up to about 5 to 10 miles across. An affine model is actually going to do the job if you have anywhere from like 20 to 50 control points for a typical ground survey system. The need to move up into those higher order polynomials typically only comes in when we start going far enough across the surface of the Earth that the Earth's curvature actually starts to play with things. Second order polynomial is basically the highest order of math that I've ever needed to use working on any of these local systems. And so for that system I mentioned a few minutes ago, where we had a grid that was about 11 miles across, that one required a second order polynomial. Sometimes if you have significant distortion over a localized area, you might need to step it up to second order polynomial, but most of the work is going to take place down on the affine polynomial. Third, fourth, and fifth, those are very useful when we start talking about extremely large areas, very, very large regional areas with very high numbers of control points as well. So again, just on the basic level, I would typically start with an affine, examine some of the error values that we're going to be taking a look at in just a minute, and if the affine doesn't do quite a good enough job, then step it up to second order and see how that improves. So today we're going to be working with some pretty typical data. An affine model is going to do just fine for this local stuff that we have here. And then we get on to the outputs, the column outputs that we have here. What we're really after is an equation, but to describe the accuracy of that system, we have some various outputs that we have. So the northing error and the easting error are basically the errors relative to the local coordinate system. We have a northing reverse error and easting reverse error, and those are going to be errors relative to our control points, whatever we have. in there. So I've gone ahead and added in these placeholder columns already. You can see that you typically use those abbreviations. You can call those columns whatever you like there. Some folks like to use the full words. Usually the abbreviations are good enough for the work I'm doing. Down at the bottom is our last setting there to automatically flag any errors greater than a certain multiple of either the input units or the root mean square error. Now the math that we're doing is basically getting into things like least squares. We're going to be calculating those error columns that we have above there. Those are going to be what we call residual errors of the fit of those two systems to each other. I typically like to work with the multiple of the root mean square error. Some folks like to work with a multiple of an input unit. That allows you to set basically an overall accuracy threshold of a linear distance. I like the root mean square error more because it scales to the scale of all of your data together. So if you have very loose data, it's not going to flag everything in your first time through. It's actually going to be a little more helpful in that first assessment of your data. So I'm going to leave that set on 3 times the root mean square as we're going. Let's see here. We've got a question coming in about which math transform would I use if I need to derive a typical 7 or 9 parameter transformation, 3 translates, 3 rotates, and 1 to 3 scales. If you are let's see, if you're talking about a datum transformation, that's actually going to be a slightly different function. You'll also see there's a datum transformation derivation down at the bottom for a 7-parameter transformation. I have to admit I'm not familiar with a 9-parameter transformation with multiple scales in there. I assume you're talking about scales in the x, y, and z directions. But I'm going to go out on a limb and make a guess here, and I believe getting close to what you would be referring to as a 7-parameter transformation in a grid-based transformation would probably be in between either the affine or the second-order polynomial to get similar levels of accuracy between those types of parameter collections. If that's not a clear enough answer for you, definitely follow up with us via email at geohelp@bluemarblegeo.com. And we can hopefully go into a little more depth on that part of the discussion. So I'm going to OK my settings here, and we're going to come back to our main interface. Now, assuming we've got all those columns in place and we've identified our output coordinate system for our control, in this case our UTM system, we've identified that properly, we can go ahead and hit calculate. And we should see a whole lot of very, very small fractions fill into those residual error columns. Visually, that is practically impossible to read. Each error vector, we have both a north error vector and an east error vector that combine for each of those points in the forward and the reverse directions. Very, very tricky to read. It's much, much simpler if we examine these graphically. And so we have a tool designed just for that purpose. It only enables immediately following a best fit calculation. It's right there below the grid, labeled Display Error Plot. So what this does is it takes all of our control points and sets them into a relative position to each other in both the local coordinate system and in the control coordinate system. So if you're working with very significantly different data, you might actually see different layouts of the points relative to each other on the forward and the reverse direction. In mine, they are very, very tight, very, very close together, and so we're not going to see a whole lot of perspective difference between those two, since I'm working in UTM and another local linear system. Now, each of the green dots that we have on there is the relative position of our control data. The error vectors that are coming off of those are not a true representation of both of those north and east residual error directions. What those are basically multiplied or exaggerated values that we have in there. So we're adding a little bit of help into the process simply because if we were to map up the actual relative distances on those tails, you wouldn't see most of them with typical survey control data. So I'm going to point out a couple of numbers that we have on screen here. Over on this panel called Error Plot Details, you're going to see the root mean square error, and that's essentially the overall error for the entire model. That you can sort of think of it as the average error for all of those point collections. Beneath that, this is going to be in the local units that we're working in. So in our case, our coordinates are in meters. So we are looking at a root mean square error of about 10 centimeters for the overall model. You're going to see an exaggeration factor, and that exaggeration factor is something that the calculator is just coming up with to put meaningful lengths on some of those error vectors. So typically, the higher the exaggeration factor you have, the lower the root mean square error you're going to have. So a bigger exaggeration factor is kind of a good thing, because we're having to multiply all those errors by a bigger amount to make them actually stand out on the page to you. Lastly, there we have the residual max, and so each individual error is called a residual error for each of those points. The residual max is the highest of any of the errors for the points. So ideally, we want to get our residual max down fairly close to our root mean square error. So if we have very little variation in there, that's a good thing. That means we have a nice uniform model over the whole area. So looking at our map here, we have a couple of kind of obvious points that have some big tails, and I'm just going to use the highlighter in GoToMeeting to point some of those out. So we have this guy here, we have this guy here, and we have this guy here. Those are kind of some of our bigger tails that are sort of jumping off the page at us. So what we need to do is take a look at the actual numbers behind those errors. So what I can do is in my, let's see how I shut the highlighter off, there we go. If we use our selection tools that you'll see up on the error plot toolbar, we can click on any of those and you'll see them blink red as you make those selections, and you'll see the selected feature information change as you click on each of those. So let's just take a look at this one right here. That is identified as point R21, and if you remember, that's because we don't have any identification information assigned to these individual controls. So this is the point that's in row number 21. That's how we're going to pick that out. We can see the X and Y coordinates in its local space. We can see the UTM coordinates that goes with as well. We have the X error and the Y error both individually separated out there. So here's where I'm getting that 0.2693 meters. That is corresponding with our residual max. And so there is the possibility that that could be a bad point. We have the same type of information there for point number 20 and point number 7 as well in our table. So we have a few points here that we could question as being maybe there's just a problem with some of those points. Maybe it's a systematic problem. Maybe it was a simple transcription error. Somebody was writing down those values from the survey. On one sense, it doesn't really matter where the error comes from, but we may want to either correct, to resurvey, or to simply remove a control pair from the overall model. So I can see that point 21 there is our worst error. So I'm going to start by removing that from the model. So I'm going to close out of my error plot. I'm going to go down to my table. I'm going to find row 21 there. And this is where the point use flag switch comes in. We're going to take the 1 that is in the point use flag, and we're just going to change that over to a 0. This is essentially just a little binary switch that we have in the table. By putting a 0 in there, that's going to take that out of the model. We can go right back down at the bottom and recalculate that. And when the calculation is updated, you'll see all of those residual errors are going to change just very, very, very slightly. Most of them are going to go down, and the one that we've taken out of the model is now actually going to go up because it's not actually being factored in to the rest of that model. So we'll refresh the error plot. Take a look at that. You'll notice the symbology changes for the points that we exclude. They turn black and we change it to a little triangle symbol. There is also a legend that sometimes appears here on the error plot. I typically shut this off once I've gotten going, just to help have more space to look at the selected feature information. But those will give you a little key to points that are either flagged as errors or if they're going to be factored into the solutions. I'll just shut that back off again. And we can see that by eliminating that point number 21 in my list, we've dropped our residual, rather our root mean square error of all the residuals. We've dropped that down. It's improved by a little more than a centimeter. And our residual max has also improved by about 3 centimeters. Still, the residual max is, a little bit above the root mean square. We could go back and check out some of those other systems. We could check out point number 7. We could compare the error from point 7 to the error from point number 20. We might remove those individually, put 21 back in there, do some comparisons. Generally, we want to remove one at a time. We might want to remove one, put one back in, do some of those comparisons, and that will help us figure out if we have a systematic error in a certain region of the data, or if we maybe just actually have a single bad point for a region. In practice, if you're really concerned about precision on some of these, we're possibly even going to need to go back out into the field to double check some of these. Typically your survey control isn't something that you're going to establish just kind of willy-nilly. It's going to be something that a lot of work goes into, so the odds of having truly bad points in there are not terribly common. But every once in a while it does take a little bit of ground truthing, a little bit of double checking with your survey team to really nail down some of those fits. But the process is essentially similar here. We're going to do the fit. We're going to compare the residuals, the root mean square for the whole thing, the individual residuals, and we're going to try and dial that down so we have a very uniform model that has a residual for the whole model. That's a nice low number within the tolerances that we're looking for, and a nice low residual max that implies that we have a very uniform fit throughout the entire area.
Sam, what kind of accuracy do you think we can expect from these?
Okay, so that's one of the also very common questions that comes along from these. The accuracy is going to depend directly on the source data that's going in. This is going to be just about as perfect of an example of garbage in, garbage out. If you have poor quality survey data that's being fed into these, you're going to get a poor quality fit. If you have typical high-quality survey data that is extremely accurate to the localized areas, it's definitely possible to get transformations for these that are well within tenths of an inch and things like that. So very, very common systems used by surveyors are dialed in to nail those residuals down within tenths of an inch of transformation accuracy. But it is 100% dependent on the data that goes in and how good that data is compared to the overall scale of the systems. If you have loose data over a very large region, obviously that's going to suffer. But you can come back and do some quality checks once you've established the transformation against known control and unknown control. So you find yourself some arbitrary locations, you survey those, what your expected local coordinates are versus what your calculated local coordinates are, and that's really sort of the final step to figure out just how good your accuracy actually is delivering on these. So now, assuming that we've eliminated any of our bad points, we've gone out, we've resurveyed, we've established control that we're pretty happy with, the last steps here are to finalize your coordinate system. Now, the new fitted coordinate system that we have here, again, that's just our placeholder name. We can right-click on that and go directly to Edit, and that will allow us to go up to the name of that system, and we can put in whatever title we want. A lot of these are going to have a natural geographic name based on whatever mine or whatever airport you might be working on. I'm just going to call mine Sam's Local Grid. And when we OK that, the only thing left to do, aside from rename that, is to go into our data source menu. pick the coordinate system definitions themselves, and we're actually going to find that in the fitted category of coordinate systems. So you're going to see the one local grid that I've got derived here. I can crack that open and have a look at all of the parameters that define that polynomial, whatever level of polynomial we've chosen, whether that's going to be an affine, second order, or anything more complex than that. If you like, you can also fill out the remarks on there with your own remarks. A lot of folks will put information there on the number of control points put in there, things like the residual max, the root mean square, the source of any control data. Sometimes that data comes from a document that will be maintained on your local networks if you're working at a large organization. Any other information you want to put in there in the remarks as well. You can also come directly to this dialog to make that name change if you like. But the only thing you need to do to make this permanent on your system is hit save right in here. So we're just going to go ahead and hit save. It's going to ask you to verify that you want to save that into your custom database, and all you have to do is say, yes please, let's save that into our database, and that is then permanently a part of your calculator workspace. That can be exported and shared with other users of the calculator. But more importantly, it allows you to apply that to any type of data that you can convert in the calculator. So to finish up our process here and to wrap it up with our last work steps, I'm going to switch this back to a conversion. And we're now going to see if we can recalculate our local control points or rather our geodetically based control points from our local grid with this new affine transformation that we just had. So I'm going to go into my column settings, and because I'm doing a conversion, this is going to be a little bit different looking now. I'm going to take my local northing and local easting coordinates, and I'm going to insert some new columns in here, and I'm just simply going to call those my calculated north, and I'll insert that ahead of my UTM coordinates here, and I will add in a calculated east. And I'll insert that in front of my UTM coordinates as well. We'll see some new columns light up in the table there. And then all we need to do is go ahead and hit calculate. Hopefully what we have are coordinates that are very, very similar to our actual controls. And in this example, based on, again, this is real survey data, we're actually getting dead on for most of that. We're getting down within that last centimeter. And if you go all the way down through here, you'll see a couple examples that don't. You'll see a couple examples that are off by 1 or 2 centimeters. And those are simply going to be because some of that grid is going to be a little less uniform than some of those other parts. This is where the establishment of the best possible controls comes in. If you want every single point to be dead on in there, that might involve some legwork, getting your survey team back out there to button up the relationship between some of those points. If you have a very, very loose fit in there and you have sort of systematic errors where you see all of those error vectors facing off in the same direction, maybe you've got some curvature in there. So maybe you want to try stepping it up to a second order polynomial, or simply adding in some more control points to get a more complicated model put together. So that's the general process for establishing these transformations. And let's see if we have any questions.
Yes, we do. Does this support 3D transformations?
Okay, so what we've been talking about so far is purely a two-dimensional transformation between one horizontal local grid and one horizontal geodetically based grid, whether that's lat long or some projection. This function is 2D only. We do have another new function that we've just added this year that allows us to actually model the rest of that to get the third dimension going on here, and that is actually going to be covered in another session that we're going to be doing. Since it is its whole own complicated workflow, takes local elevation data. We can start with essentially the same style data that we have here in our local system, and it's also going to factor in elevations. The process will essentially be deriving your own geoid surface That's going to do a little bit of work over in our other application, Global Mapper. We're going to bring that data then back into the calculator to interpret as a grid, so a local geoid grid. Within the workflow that we've covered today, this is a 2D process. Extending that workflow a little farther, we can actually bring in that third dimension, and keep your eyes peeled on our upcoming webinar topics, because that is going to actually be the topic of completely its own session. It is a rather longer and involved workflow, just like this one is. Let's see if we have any other questions that have come in through the control panel here. Okay, it looks like we've
covered them all.
Covered some of those. So it looks like we might have one more.
Okay. Can I use this on any kind of data once I derive the transformation?
Yes. So the data, any of the data types that we can convert anywhere in the Geographic Calculator, this local best fit system can be selected. So you'll see a fitted coordinate system option in any of our pickers. I can go back to our interactive conversions. I can go to select a coordinate system, and you'll see under the fitted category, your local grid is going to appear both in the to and the from. So your source and your targets, you can use your local coordinate system in any of those. The one caveat that does apply to some of that is that when you're outputting in local coordinates, depending on the file format you put out, the description of that system isn't going to match other software. So if you're going to be taking this into a GIS system and you're going to want to work with those local coordinates in another GIS system, just be ready for that to not be recognized, because it's an alien coordinate system to those systems. They are not geodetically based. It is purely a transformation, but they can be interpreted inside the calculator. And typically, if you're going to be moving to various systems, you're going to be starting in your local grid, and you're going to be moving to something geodetically based.
Okay, looks like that spurred on another question. Can you export this transformation to ArcGIS?
Okay, so yeah, that's a natural follow-on from what we were just talking about. The system itself is a polynomial description of a transformation. So unfortunately, most GIS systems are not directly capable of digesting the parameters for those transformations. So typically the question was specifically on ArcGIS, and I'm going to generalize that to say any GIS system. Those are typically requiring things that are based on either a true projection or a latitude-longitude type system. So to take the transformation out of here, it's not possible to get that into most other GIS type systems, GIS or CAD type systems, because they just don't have the guts under the hood to be able to understand the affine transformation in relation to projections. So what most folks are going to be doing with this is doing your transformations in the calculator, preparing your data into a true projection. Or if you're working in that local grid, you can put it into the local grid and take the data itself out to a GIS system. It's just that when you get there, you're going to be working in, they have a few names, but it'll either be local coordinates or non-Earth coordinates, or sometimes it's called Earth coordinates. But essentially, however that application is going to deal with data that is not in a recognizable projection. So it's typically easiest to do most of that work in the calculator, export the data that you're going to be working into either ArcGIS, Global Mapper, MapInfo, AutoCAD, any of those other packages where you're doing the spatial mapping portions, doing the transformations in calculator, getting it ready, and then taking it over all in some unified coordinate system, whether it's your local space or a projected space. So I think that wraps it up for the questions that have come in. Again, if you have any further questions that you think of, If you're watching this in the future on YouTube, if you have any questions about anything we've talked about, definitely go ahead and send those in to us at geohelp@bluemarblegeo.com. Again, you can find the links to all of those resources, our Blue Marble user conference page, again coming up in October, our webinars archive, YouTube channel, are the upcoming conferences that we'll be at all across the country and across the world. Thank you everyone for tuning in today. Thanks Josie for joining me.
Great, thanks Sam.
And we'll see you next time.